This is Professor Karri Dipetrillo. She did her undergrad at Brown, and she received her PhD at Harvard. That's where we actually met during that time at CERN, when we were both stationed at CERN as graduate students. And then she moved to Fermilab as a Lederman Fellow before joining the faculty of the University of Chicago as a Neubauer Assistant Professor. And very looking forward to hearing about the future of our field.
Thank you very much for having me. So I'm going to be talking about sort of a long-term future of particle physics and a possibility for it. And I know that colloquia are more general audiences, so I kind of want to frame it by starting with by framing it from two questions that I actually got from an Uber driver on the way back from O'Hare. She asked me, is it, oh, we're coming back from work or vacation? I said, oh, I'm coming back from work. We're doing long-term planning for particle physics. This was part of the P5 process. And she said, oh, that's so interesting. I love particle physics, because she was near the Fermilab area. She knew all about all the stuff that was happening there. And she said, you know, we're kind of the same. Like, I'm an artist. Like, what are you talking about? She goes, well, we're both concerned with what are we made of and how did we get here? Those kinds of philosophical questions. And we seem to answer them and address them in different ways. And so I think when we talk about particle physics, this is one of the main pictures that we're thinking about. What are we made of? We want to understand the smallest, most irreducible pieces of matter, fundamental particles, and the forces that govern those particles. And part of the idea is that if we understand the fundamental particle content of the universe and the forces that describe them, we can also, I'm going to learn how to use the pointer, I swear. We can also kind of map this back onto the early universe, right? If we understand the various phase transitions that matter goes through as you go to lower temperatures, because the universe is expanding, we can extrapolate backwards and hopefully make predictions that we see out there in the universe. Or maybe we see something in the universe that we don't currently describe with particle physics. And that teaches us something too about what to look for. So this is, I think, where colliders are really uniquely powerful. It's really, in my opinion, our only tool for doing controlled experiments that directly probe smaller scales, right? The higher in energy you go, the smaller distance scale you're probing, and recreating the conditions of the early universe in the laboratory. Similarly, the higher in energy you go, the earlier in the universe you're probing. And this approach has been highly successful, right? Over the past 50 years or so, as we've gone to higher and higher energies, we have discovered more and more particles. This has enabled us to establish and test the standard model of particle physics. This is our best known understanding of the particle content of the universe. However, there are several questions surrounding the standard model. If I look at the particle content mapped out like this, there are several pieces that we don't understand. One is the most recent particle we discovered, the Higgs boson, I think raises a lot of questions, some of which I'll talk more about. We don't understand the origin of the neutrino mass and the neutrino nature. I look at this and I think this is very reminiscent of the periodic table of elements, which has some deeper underlying, this underlying pattern points to a deeper structure. And so maybe the same thing is going on here. Maybe there's another scale that's even smaller that will help explain why the standard model looks this way. We also know that it's incomplete, right? So when we look out into the universe, we see evidence for dark matter. We also have no explanation for why there's no more matter than antimatter. And there's no particle explanation for gravity. Okay? So we know that there is more out there and that the standard model is not complete. So how can we use colliders to answer these kinds of questions? Here I have kind of a map of the energy frontier, looking a little bit in the past and a little bit in the future, really dominated by the Large Hadron Collider in Geneva, Switzerland. And so if you think about the LHC schedule, what we've learned and where we're going, in run 1, we discovered the Higgs boson. This was quite exciting. In run 2, we doubled our energy. And we didn't see any signs of beyond the center model particles at the LHC or elsewhere. And we were kind of expecting to. So nature started to look a little bit more complex than we were thinking originally. And if you think about where we are today, we're towards the end of run 3, really preparing for the high luminosity LHC, where we're going to increase the size of our data set by about a factor of 10. And we're completely upgrading our detectors and our trigger, our sort of data acquisition, or how we make decisions about which events to save. And this will enable us to fully explore the TeV scale for a wide variety of phenomena, rare processes we haven't been able to look at before, but we're still probing the same sort of energy range, energy scale. We know that the high luminosity LHC is also slated to run until 2040. We think about the long timescales and costs associated with colliders. It means we need to already be preparing for what comes next. And so there's been a lot of long-term planning processes in particle physics in the US and Europe and Asia, which are trying to answer this question of what should come next, what should we build? And so it's really important that we are, as physicists, continually evaluating the science case for future colliders to help decide what to build, and making sure that we're addressing accelerator and detector needs to be able to do that physics when it comes time. Okay, so I want to make the case for why the next energy scale of interest is the 10 TeV scale. So this is an order of magnitude more than what we're probing at the LHC. And so the first kind of example that I want to give has to do with the Higgs, right? So colliders are the only place we can produce and characterize Higgs bosons. We know that Higgs exists, but there's still a lot we don't know about it. Is it a standard model like Higgs? It has something to do with the mass of our standard model particles. Dark matter is likely a particle that has mass. Maybe somehow the Higgs is connected to it. It's deeply connected to phase transitions in the universe, which I'll talk about. But all of these questions are really central to particle physics, right? And so having a machine where you can produce Higgs bosons and make quantitative statements about the Higgs is very important. And so just to sort of give some concrete examples for why we care about the Higgs, thinking about the questions, what are we made of and how did we get here? We exist because of electroweak symmetry breaking, right? So in the early universe, sort of the Higgs was sitting at, the Higgs potential looked something like this, and we're sitting at a minimum of 0. As the universe expands and cools, we have some phase transition where we go to a non-zero minimum. We don't know a lot of the details about that exact phase transition. It's very interesting to us. But we know that because the Higgs gives mass to fundamental particles, this is essential to how we exist, right? Electrons having mass is essential for them to stay around sort of atoms. In terms of thinking about how we got here, the exact nature of this phase transition is extremely interesting to us. One of the conditions for baryogenesis is having a first order phase transition, sort of where you're tunneling through a potential. So the exact shape of how this happens matters a lot to us. Different particles in the standard model have different masses, right? So like the electron has a different mass from a muon and a tau. Does this tell us something about the origin of flavor? If, like I said before, if the Higgs is giving mass to standard model particles, maybe it's also giving mass to dark sectors. Maybe it's a portal to a dark sector. And this Higgs potential also allows us to make statements about the stability of the universe. So it has deep connections to the origin and the end of the universe. Okay, so some specific questions that we want to try and answer at the 10 TeV scale. The first is the microscopic nature of the Higgs. This is a seemingly standard model fundamental spin 0 boson, which means its mass is highly sensitive to quantum corrections and should be pulled up to kind of the next energy scale of interest. But we don't see that. We observe a mass of 125 GeV. So what new physics is preventing the mass of the Higgs from being pulled up to the Planck scale? Is, for example, there a new symmetry, like supersymmetry, which predicts additional particles? Or is it a composite Higgs, like the pi is a composite particle, And we have a next kind of energy scale of interest, which also predicts additional particles. And so if we look at the data we have collected at the LHC, we have looked for these kinds of models, these additional particles which are predicted, and we haven't seen them yet, right? Many people will probably show you exclusions of supersymmetry models, and looking for composite particles, and exclusions go sort of up to about TeV, maybe a little bit higher. So data is telling us we need to look at a higher energy. And if we look at the Higgs mass itself, in complete models like supersymmetry, a mass of 125 GeV is very suggestive and tells us that maybe the particles that are kind of protecting the Higgs mass are at the multi-TeV scale. And so getting to something like 10 TeV would enable us to kind of fully probe this expected phase space. Like I said before, we're very interested in the Higgs potential and understanding its shape. And so if you think about what we've measured at the LHC so far, the Higgs mass, this is just kind of the minimum of this potential. We don't know its full shape. And if I'm doing fake physics and thinking about this like a Taylor series expansion, we also need to measure the trilinear coupling and the quartic coupling, the self-coupling of the Higgs. And the way that you do that is with multi-Higgs events where you're producing 2 Higgs bosons or 3 Higgs bosons. This requires a lot of energy. And so if you're thinking about your uncertainty on the Higgs potential, this is about where we are with the LHC. When we get to the high luminosity LHC, we'll get to an uncertainty of about 50 to 20% on the trilinear coupling. And when we get to the 10 TeV scale, we're producing enough Higgs such that we can measure this at the percent level. And this tells us a lot about the shape of that potential and the early universe itself. The 10 TeV scale would also enable us to test electrode restoration in really interesting ways. And I think there's a lot of interesting theory and phenomenology about ways to do that. So then the second reason that I want to talk about is dark matter, right? We know it exists, we don't know what it is. And I want to make the case that colliders play an important role in understanding its nature. So if we think about why we care about dark matter, what are we made of? You know, there's 5 times more dark matter in the universe than there is visible matter. And if we think about its role in how did we get here, galaxy formation, clustering, like the shape of the universe that is around us, this has a lot to do with dark matter, right? Our universe would look very different if it didn't exist. And in fact, early galaxies would be stripped of their heavy elements, and life as we know it wouldn't exist without dark matter. So we also owe our existence to it. So if we think about the simplest dark matter candidates, weakly interacting massive particles, very often people will go around saying, WIMPs are dead. You know, we've completely excluded them. Dark matter must be more complex than that. But this isn't true. So if we think about these thermal WIMPs, this is the simplest explanation for the observed universe. And we have, based on the number density that we observe, we have these 2 simple models where you have either a Dirac fermion doublet or a Majorana fermion triplet, the Higgsino and Muon of about 1 TeV and 3 TeV. And we have not touched these at all. We have not gotten there. And so you can see this is from direct detection dark matter experiments, sort of thinking about cross sections as a function of mass. You can look at operating planned and sort of further future impossible, we don't know how to do it experiments, and see that if the simplest WIMP, simplest dark matter candidate, the Higgsino as an example, were dark matter, we would not be able to see it at all anytime in our future. If we think about indirect detection, you do a little bit better. Okay. You may get a hint of a Lino with current experiments, certainly with medium term, so like 10 plus years or so. But you need kind of very long-term collider timescale indirect detection experiments to fully cover this phase space. And I would also argue that if you get a signal in your indirect detection experiment that's pointing to a TeV or a 3 TeV WIMP, you're going to want to study it in a collider. And so the only way to really do this is to get to sort of the multi-TeV scale. So this, having a 10 TeV collider would allow you to make definitive statements about the simplest dark matter candidates out there. Okay. So I hope I convinced you that we have a new scale of interest. Why should we collide muons to get there? Let's think about our traditional paradigm. So if we think about what we've done throughout history, we've done the simplest thing that makes the most sense. We take the stable standard model particles that are all around us, accelerate and collide them. So if we think about electrons, this is great because they are fundamental particles. All of the energy from the beam goes into the collision. It's fairly low background. The challenge is that because they have such a small mass, they emit a lot of radiation once you accelerate them. It's very hard to get to high energies, in particular at a circular collider. So we associate this with lower energy precision machines, like we would call this a Higgs factory. For protons, they have a larger mass, which means higher energies are achievable. We haven't really had to deal with synchrotron radiation for protons yet. The challenge with protons is that they're composite. This means that if you're thinking about the energies of the LHC, you're probing distance scales smaller than the proton itself. You're colliding the quarks and gluons, which only carry a fraction of the proton's momentum. And so this means that you need a higher energy beam than, say, the collision of the particle that you're trying to probe. And because you're colliding these quarks and gluons, you have a very high rate of messy QCD backgrounds, like soft multi-jet events. But so traditionally, that means we associate protons with energy, but not precision. And we've always had this dichotomy.
Sorry, but also one advantage of this messiness is that proton machines are discovery machines because
you're probing all. Yes, but I will make the case that once you get up to about a TeV with electrons or muons, you also have some similar features. It's a great point. Certainly, I am spoiled by working at the LHC and being able to probe a wide range of energies at once. The idea of sitting on the Z mass for years and then ZH for years is kind of terrifying to me. Okay, so how do we get to higher energies? So in this traditional paradigm, you can kind of take a fixed technology, maybe increase your accelerating gradient, increase your dipole strength, and go bigger. So if we think about, say, proton machines, which are kind of our best way to probe high energies now, this means that you need to scale up the size of your circle and also the field strength of the dipole that you use to bring your protons around that circle. So if we think about the dipoles in the LHC, what size machine do you need to get to 100 TeV proton-proton collider, the 10 TeV scale? You need something close to 200 kilometers. If you think about sort of the record magnets that we've produced, this is niobium tin. This is brittle and very difficult to industrialize. That gets you to about 100 kilometers. If you're thinking about future high temperature superconductors, which is very much in early R&D, this is about 80 kilometers. So this tells you something about the scale of the next hadron machine that we would be looking for. And this is what is proposed as sort of a long-term future for CERN. I think there's a reasonability question of, is a 100-kilometer machine really feasible? What does that mean for humanity? Maybe it is, but certainly whatever comes after that is not feasible. We can't extend all the way up to here. So I think this motivates already thinking about a different approach. So muons break this traditional electron-proton precision energy paradigm because you have massive fundamental particles. So this means you're not suffering from synchrotron radiation. You can have a small ring that's at high energy without your muons losing energy and radiating away. And all of your energy is going into the beam. So you just need a 10 TeV collider. And this is what gives you really the small footprint with respect to other higher energy proposals. So here we have the LHC compared to CLIF. This is a linear 3 TeV E plus E minus collider proposal that's 50 kilometers long. The proposed 100 TeV hadron collider compared to the muon collider, which is smaller than the LHC and also conveniently would fit within the Fermilab site. So it's a very exciting potential future for the US. And at CERN or Fermilab, it would also be building kind of on existing proton infrastructure. So this is all very attractive. Not only is it compact, it's also power and cost efficient. So if you think about the luminosity as a function of wall plug power and how this evolves with energy, circular E plus E minus colliders, because of synchrotron radiation, your luminosity is dropping rapidly, something like energy to the 4. Linear E plus E minus colliders tend to be about flat. But with muons, because you get time dilation, you get a longer lifetime at higher energies, your luminosity per power actually increases with energy. This is the only machine that does this. You can sort of think about how this maps onto your costs, which scales with, say, site power, the size of your collider, because you need to dig a tunnel and you also need to fill it with all of your components. And C, sort of for our highest energy collider proposals that are on like a 20-30 year time scale, we have the lowest power consumption and also the lowest projected cost. So this is all stuff that makes us very excited. It makes it a much easier sell, I think, to funding agencies if your dollar investment is going to technology instead of a big tunnel. In terms of the physics, so not only is it both kind of a, we say it gives you the benefits of protons and electrons. This is also true in terms of energy and precision in the same machine. So you have two production mechanisms at a Muon Collider. Once you're, say, above about a TeV in center mass energy. The first is this S-channel diagram, where your cross-section will drop pretty rapidly with energy. But this would be kind of a primary discovery mechanism for high mass particles, like you'd be pair producing SUSY particles, for example, and have access to a wide range of energies. Something that happens above about a TeV is that your muons start to radiate vector bosons, so W's and Z's, and you get this sort of, 100 GeV scale vector boson fusion production mechanism. And because this process actually increases, the cross-section increases with energy, and you have very low backgrounds, right? You don't have a massive QCD background, which is orders of magnitude larger than this kind of process. This means you're able to do precision electroweak physics in a relatively clean environment. We can think about how this maps onto sensitivity to new physics, comparing to 100 TeV collider specifically. And so this is just to show that if you're thinking about these 2x2 processes, so pair producing new particles, roughly a 10 TeV Muon collider is very similar to a 100 TeV hadron collider. There is some subtlety about if you're looking at electric production versus, say, a colored particle with QCD style production. There, a hadron collider tends to win out in terms of directly producing those particles. But if you think about indirect reach, so looking for tails and the deviation of, say, your distributions, actually the Muon collider wins out by quite a bit. It gets a 10 TeV Muon collider gets up to, in many cases, something like sensitivity to 80 TeV, kind of new physics effects. Whereas your part-time luminosity with protons drops really rapidly with energy, and you have much less sensitivity overall. So there's some subtleties here, but let's say all things are about equal, they're complementary. In terms of electroweak precision, like I said, just to make some comparison to other collider proposals, you get about 10 to the 7 signal Higgs events, which means your uncertainties on, say, Higgs couplings to other particles is competitive with E plus E minus 6 factories. And you get about 10,000 di-Higgs events, which means you can measure the self-coupling with uncertainties comparable to 100 TeV. And we've done this in full simulation, whereas nobody has done a full simulation 100 TeV study whatsoever. So they have not addressed backgrounds at all. Something else that's really exciting is not only would we be able to study these deviations in terms of Higgs couplings with precision, we would also be able to look for the new particles that are causing those deviations in the same machine. I think something else that has a lot of early career physicists very excited is that there's a lot of potential for physics along the way. So one thing that's very exciting is that straight sections of either, say, the accelerator complex or the collider itself give you kind of the perfect neutrino beam. So if you think about muon decay, it's this process. You know exactly the fraction of electron, muon, and neutrinos. You know the energy spectra and intensity. This is in contrast to, say, producing neutrinos with a proton beam on target and pion decays, where you maybe have a mix of kaon decays. And understanding the flux and the composition of the beam is very difficult. All of the sort of, proton accelerator complex that would get you a muon beam may also give you an opportunity to do low mass dark matter or dark sector searches. A lot of the, I think, technology R&D will also have synergies with charged lepton flavor violation experiments like Multi-TeV or G-2 and things like that. Okay. So I hope I convinced you 10 TeV is a scale of interest. Muons are a great way to get there. Now the question is, can we build it? So all of the challenges associated with the Muon Collider kind of have to do with the muon lifetime. So the muon decays in the rest frame in 2.2 microseconds. This means that we need to produce muons. We need to cool them. We need to manipulate them into a small bunch or a small beam before we can accelerate them, which we also have to do rapidly, and collide as many muons as we can before they decay. Muons are decaying throughout this entire process, including inside our particle detectors. So this also creates a challenge for the detectors. And so I'm going to talk about some of the challenges along the way to the detector, but maybe don't take my word on it, read the paper, because the detector is very much my area of expertise. Okay. So if we think about our design requirements, right, this always comes back to the physics. So let's say our physics goal is to measure the di-Higgs cross-section to get at this Higgs self-coupling with a few percent uncertainty that tells us exactly how many di-Higgs events you need. And if you want to produce those di-Higgs events within some number of time, you want to be aiming for about 10 inverse out of 1 in 5 years. This tells you, again, what instantaneous luminosity you need, which tells you things like how many muons per bunch, how often do you need to be colliding those bunches, what's the size of the beam. So since we're muon limited, what we do is we set the number of bunches to 1 and maximize the number of muons per bunch. So we put all of our muons into one bunch per beam and we're just circulating it and it collides kind of once or twice. We want to maximize the number of collisions that we have before the muons decay. So that means we want as small of a collider ring as possible, aiming for 10 kilometer ring for 10 TeV machine. We want to minimize our beam size. So this tells us something about the cooling process and how small we need to get our beam before all the muons decay. And then even at high energies, muons still have some lifetime. And you want to re-inject a new bunch of muons roughly once half your muons decay. So that's roughly every 100 milliseconds. And so this, you can extrapolate backwards and map these needs onto your proton source, your cooling, etc. But this is kind of roughly the principle that people follow. So your proton source, we roughly expect that you need 2 orders of magnitude more protons than you would need muons in your collider ring. And this has to do with converting protons to muons and then also muons lost in the acceleration process. So you want to deliver about 2 times 10 to the 14 protons on target. This is roughly the ideal energy to sort of maximize your muon cross-section. And then the rate is set by how often you need to refill your machine. And so what this winds up requiring is a multi-megawatt proton source, of which we are starting to see around the world as spallation neutron sources. You need a target that can withstand all of that radiation and not, collapse onto itself or be destroyed. And you want roughly a 20 Tesla solenoid to capture your muons. Which we are seeing this sort of, right? This is not unlike an hour-high magnet. Okay, so then you've produced your muons. It's roughly a basketball-sized cloud of muons with momenta in every direction. And so you need to convert this into a compact bunch, like I was saying, roughly a few micron by a few micron in the transverse direction, within about 1 kilometer, because otherwise you're losing more than an order of magnitude of muons. And so roughly, the way that this works is, say you send that basketball through a low Z absorber. So this minimizes multiple scattering while removing momenta in all direction. And then you're re-accelerating with an RF cavity. And you need to do this over and over and over again, as many times as you can within a kilometer. This, of course, this would cool just in the transverse transverse direction, so in X and Y, but not in Z. And so there's all kinds of tricks you can play with magnets to get the longitudinal cooling as well. There are designs in simulation which suggest that we can do this in some very preliminary tests, but I would say a lot more work is needed to demonstrate this in a way that would convince the community. Okay, so then you have a tiny bunch. And what you want to do is ramp up to as high energy as possible, as quickly as possible. So you need fast ramping, normal conducting dipoles to, within a single ring, get up to as high energy as possible, and then bring it to the next ring. And so the idea here is to reuse as much existing infrastructure as possible, right? So reuse Linux, reuse collider rings, but fill it with these fast ramping, normal conducting magnets. The fact that you're using normal conducting magnets means they typically don't have as high field as, say, the magnets, the superconducting magnets in your collider ring, and that's why you'll often see a larger accelerator ring and a smaller collider ring where you're putting your max field superconducting magnets in. Okay, so that's roughly the concept of how you would build a Muon collider. Coming back to this question of can we build it? So I think, let's say as much as 10 years ago, there was this concept of you need 10 miracles to build a Muon collider in terms of technology. There has been quite a bit of technology development in terms of getting the magnets that you need for the various stages of, say, this proton driver complex. The cooling, the collider, etc. You are starting to see multi-megawatt proton sources and targets, and you're starting to get sort of fast ramping magnets, superconducting magnets at the field strengths that you need. Something else that has happened is that you are seeing designs and simulations that are meeting the science targets that you need. And this came sort of, I would say, in between, say, 2015 and 2020. And it was really useful input to, say, the long-term planning processes in Europe and the US. And so by the time snowmass happened, the most recent snowmass in 2020, 2021, the conclusion was from accelerator physicists that you could build a Muon collider on a 20-year technically limited timeline, which means with infinite money and no risks being considered, no bureaucracy. Which I think is great and got a lot of people very excited about it, right? It would certainly be the fastest approach to the 10 TeV scale if this 20-year technically timeline worked out.
Sorry, but what happened years ago? One of the objections to Muon colliders was that muons decay and produce neutrinos, and that the energy of a Muon collider, these neutrinos could be dangerous for health.
Yes.
Pass through rocks, so they said we cannot build it as because it will kill the people on the French side of the Jura.
Yes.
So what happened to that?
Yes, so I have a slide with specific numbers and plots and backup. But basically just for everybody, right? Your neutrino cross section is very low, but it increases with energy, right? So as you get to higher energies, your neutrino beam will interact with material between you and the beam and produce ionizing particles. And that's the source of radiation damage that people are worried about. The thing with the Muon collider is it's such high energy, the neutrino beam is very collimated, And it's the integrated dose over a year that's the issue. It's not like you stand near the beam and there's an issue. It's if you stood near the beam for an entire year. There are ways to mitigate this. One is to put the Muon Collider underground. And studies, I think, show for a 3 TeV Muon Collider going 200 meters underground, and wiggling the beam, so pointing that neutrino beam in different places as a function of time, is sufficient to mitigate radiation and be like below Fermi-Lab site limits by, which are, if you're flying a lot, you're seeing much more radiation than Fermi-Lab site limits. For 10 TeV Muon Collider, you need to be a little bit more careful. With 3 TeV, when I said wiggle the beam, you can do this just with magnets. With 10 TeV, you want to be doing this probably with precision movers. And that's something that should be demonstrated, I think. But it's really not as bad as people tend to think it is.
In terms of competing technology, if I just want to make a linear collider, is the only like obstacle that I just need a very long vacuum tube with lots of, you know, RF sources, or is there like unknown? Do you have to solve any miracles for a linear collider?
So, I think to get to, like, with existing RF technology,
Yeah.
to get to a TeV, people say that you just need a very long linear accelerator. I don't understand the details of why something like a click or what have you would, why 3 TeV seems more out of reach or not. But people say that it does. So I would say up to the TeV scale, based on what other people say, yes. People are talking about Wakefield acceleration and possibilities there. But that, I think it was very clear from SNOMAS that there isn't a realistic collider design or path towards a collider that's in place, and more work is needed. Like, they need to approach this from a collider perspective as opposed to just a maximizing gradient for very low numbers of electrons kind of perspective. But yeah, I would say about a TeV is kind of where people are with electrons.
You also say the luminosity decreases quite quickly.
With the circular E plus E
With the
minus
circular,
collider.
okay.
So with 100-kilometer circular E plus E minus collider, the kind of maximum energies you can get to without losing more than, say, a 10% of the beam's energy each pass is about 350 GeV. So this is like a TT bar threshold.
It's one shot.
With linear, it's one shot. The luminosity tends to be roughly flat with energy, and you need to be inputting more power as you go to higher energy. I think that's one concern. Is that like the power consumption for the 3 TeV click is just like, is completely insane. Okay. So that was the accelerator side. And so I think the takeaway on the accelerator side is that there are self-consistent designs for the various subsystems of the Muon Collider in simulation with near-term accelerator technology that are really convincing for the community. Obviously, more R&D is needed, but it's enough to get us excited. On the detector side, I mentioned you have muons decaying near your detector region, which are producing high energy electrons. And there's always been this question of, can you actually extract physics in this environment? So let's think about this kind of from first principles. I said you're circulating 2 bunches and refilling your beam when depleted. Your time between collisions is roughly 30 kilohertz. This is roughly 1,000 times lower than the LHC. So this is quite nice for us in terms of detector concerns and readout. In terms of beam-induced backgrounds, this is these electron decays. If you think about decays within roughly 20 meters of your interaction point, you can just compute this based on the energy of the muon and its lifetime at that energy. You're getting roughly 10 to the 7 muons decaying in that region near your detector compared to, say, 1 collision of interest. The number of decays is decreasing with energy, and also the direction of those electrons is becoming more collimated. So that's a subtlety, but maybe a second order effect. And then the energy of each electron is increasing as you go to higher energy, and these 2 kind of effects cancel out. And this is roughly the amount of energy that you would get in your detector if you didn't do anything at all.
All right.
Yeah.
I'm missing something. The muons are equally likely to decay anywhere in the ring, right?
Mhm.
So the number of decays within 20 meters should be 20 meters divided by the circumference of the ring times the number of muons.
So the probability of a muon decaying, right?
Right, one muon will decay within 20 meters, 20 meters over the circumference.
I guess I'm not sure what you're asking.
Like, so
Sorry.
they all decay eventually, all the muons decay eventually.
You
right?
dump the bunch once half of the muons decayed.
Okay, but that's the, so 50% of muons decay eventually.
50% of muons will decay when the beam is in, when the bunch is in the ring, yes.
And they're equally likely to decay anywhere in
Yes,
the,
it's just that if you think about electrons which will reach the detector, we're only worried about decays that are happening near our detector region.
right, but so, but I'm not seeing where the energy comes in next, so it should just be like. It could decay anywhere, there's 20-meter region where the decay happens.
So if you think about muon decay, it's a 3-body decay process, 2 neutrinos, 1 electron. So kind of on average, the energy of your electron, which is the only thing that's going to be interacting with the detector, for the most part, is roughly 1/3 the energy of the muon. So the energy of your electron is scaling linearly with the energy of your beam. Whereas the number of electrons being produced, the number of decays, is inversely proportional to the energy of your beam, just because of the boost. So those two effects cancel out, and at any collider energy, this is roughly the amount of total energy produced by electrons near the detector region.
Okay, I think I'm not understanding end decay. Maybe there's another scale there.
End decay?
Yeah.
Oh, this is the number of muons decaying within 20 meters.
Right,
Right, because the lifetime gets extended as you go to higher energy.
but you also get more circles as you go to higher energy. Because
But the velocity isn't really, so your ring size needs to scale with energy.
okay, so this is when you say the energy end decay decreases energy because the ring gets bigger.
Mhm.
Okay, so it's not fixed geometry.
It's a design
Oh,
criteria.
Yeah, it's like, okay, got it. I
Okay,
understand.
all right, okay. So, sorry, so you have these high energy electrons, roughly 10⁷ of them, which could enter into your detector region. This would be massively difficult in terms of separating TeV signals. So what we do is we use tungsten nozzles, or tungsten cones, to suppress the high energy component of this beam induced background, right? So it's like having an electron interact with a very dense calorimeter and produce a shower. Until you're getting down to very low momentum diffuse, say electrons, photons, and neutrons, which survive. We coat the tungsten nozzle in a polyethylene to help capture some of those neutrons and prevent them from entering into the detector region. But roughly, if we think about it, what winds up reaching the detector is 10⁸ low momentum particles per event. This is predominantly neutrons, maybe 10⁷ low energy electrons. And when I say low energy, I mean something like 10 MeV. It's very diffuse, it's non-pointing, so it's coming in from the sides instead of being produced at the collision point. And it tends to be out of time compared to collision particles. So it looks very different. It's a daunting number, but it looks very different from signal. Okay. So besides those tungsten nozzles, a detector at a Muon Collider looks very much like a general purpose detector, very similar to a CMS style detector. And so part of the part of the snowmass process was coming up with a detector design and full simulation. So simulating the beam induced background fully through the detector, making assumptions about sort of near-term detector technology in terms of what kinds of silicon detectors we have, calorimeters, et cetera. And demonstrating that we could do physics. Then we're in a situation where we have a 3 TeV detector, just because that was kind of the simulation code we had for the beam induced background at that point, but a science case for 10 TeV. So something that has happened since snowmass is that we've come up with a 10 TeV detector design, which recently was on the archive a few weeks ago, which was very much a US driven effort, whereas the snowmass effort had a lot of, I think a lot of effort from Europe. So it's really nice to see both regions contributing kind of to the design here. Just to give you a sense of sort of how the environment compares to things which exist and sort of the technology we have on hand. Your occupancy varies between about the same as an HLLHC event, to maybe an order of magnitude higher. And that order of magnitude higher is in the innermost pixel layer. The further out you go in radius, the closer to HLLHC sort of occupancies you get. Like I said before, we're talking about something that's about 1,000th of the event rate. So in terms of readout, it's looking like we can actually maybe do some data reduction on detector, some local reconstruction, what have you, and do what's called streaming. So do some data reduction per event, but save information about every event. In terms of radiation damage, there's very similar dose influence to what we would expect at the high luminosity LHC. So this means that we should be able to build detectors with kind of HLHC technology, maybe extending to higher granularity, things like that. And just for reference, if you're thinking about 100 TeV proton-proton collider, the radiation damage is something like 3 orders of magnitude worse. We have no idea how to build a tracker at 100 TeV proton-proton collider. This is many decades away, whereas this is something that is a few iterations of sort of electronics and detector R&D away. Right, so like I said, for the tracker, the occupancy is the most challenging for the innermost radii of the fixing. And this is supposed to show the occupancy for different detector layers. And if you stare at these numbers, what this ends up telling you is you have roughly about 10,000 hits from beam-induced background versus say 10 to 100 hits from signal. And this winds up calling for, if you want less than 1% occupancy to be able to run pattern recognition to do tracking, you need high granularity. So 25 by 25 micron, this is a little bit smaller than the HLHC, and precision timing in every layer of your tracker on the order of 30 to 60 seconds. And the reason why you would want this, you can see kind of the hit time for signal in blue versus hit time for background in black and gray. So you can reject a lot of background with precision timing cuts. So this is kind of a natural evolution of HLLHC pixel detectors and timing layers. On the calorimeter side, this is supposed to be an event display of a high energy neutron and beam induced background in a sort of particle bound simulation. This kind of works out of the box with HLLHC segmentation and timing resolution. So something like the CMS high granularity calorimeter upgrade. Something that we learned in looking at the 10 TeV detector design. So as you go to high energies, you need a larger, deeper calorimeter in order to contain all of those high energy particles you're producing. It got too difficult to have this solenoid outside of the calorimeter, so we moved it inside. And this helped to reduce beam-induced background that's hitting the calorimeter. So reduced kind of our occupancy challenge, made pattern recognition easier, like clustering easier, and improved our energy resolution overall. In terms of reconstruction, we are able to kind of meet or exceed our baseline targets in the central part of the detector. The end caps certainly need work. This is a very person power limited exercise. And so you can see kind of our track reconstruction as a function of angle with and without beam induced background. Same thing for our neutron energy resolution with and without beam induced background. Reconstruction takes a long time. It's not optimized. And certainly there's a lot of room to do better. What I've found and what I think a lot of us have found is that this is really great work for undergraduates. Like that 10 TeV detector paper was primarily done by undergraduates. So it's a great training ground for getting people involved and then ready to do, say, an Atlas or a CMS PhD. Okay, so with these full simulation studies, we've demonstrated that we can do physics at a Muon Collider. And in fact, we specifically looked at kind of the scenarios I was talking about at the beginning. So this is measuring the Higgs self-coupling with a few % uncertainty. We're beating, say, 100 TeV PP collider with realistic background simulations in order to study the Higgs potential. This is that composite Higgs scenario, so thinking about the microscopic nature of the Higgs. You can see the Muon Collider here is surpassing any other proposed collider. And then this is a search for weakly interacting massive particles WIMPs in the specific signature that they would manifest as. This would be sort of like a long-lived charge, or a long-lived charge state, which then decays to a neutral or dark matter, and a soft pion, which you wouldn't be able to reconstruct. And so this is a very difficult signature to look for, especially in an environment where you have lots of hits from beam-induced background, but we've demonstrated that we can reach the sort of thermal target of 1 in 3 TeV. And of course, I mean, this is with kind of, straw man detector design and reconstruction. We think with more work in progress, do better. So all of this has generated a lot of excitement in the past few years. So going from the 2020 European strategy to the formation of the International Muon Collider collaboration, a surge in interest at SNOMAS, funding in the European Union. They have dedicated funding from a European Union Horizon grant, to a very positive outcome from P5, the long-term planning process in the US, to the formation of the US Muon collaboration, which is in progress, and early signs of funding from US, mostly private foundations starting to come in. So all of us are very excited about this. In terms of looking forward, there's a lot of work to do. It's not just generating hype. So we have a lot of dedicated R&D to do in the next few years, in particular on accelerator component and technology. There needs to be a technical design in place for cooling demonstrator. There was a call for an interim panel in 5 or so years to make a decision about whether we should invest, say, $100 million or more in a large-scale cooling demonstration. We would also need a reference design for the eventual collider, so something a little bit more serious than we have now, and continuing the detector and physics studies to help build the physics case and convince the rest of the community. We're continuing to plan for these various long-term planning processes, and we're also thinking about community building and workforce development. So for instance, this summer, we're going to have the first US Muon Collider school. So this is kind of like the US particle accelerator schools, but Muon Collider specific, to help train students and kickstart R&D efforts for them for like PhD projects. Okay, so just to conclude, I hope I convinced you there's a strong science case for a 10-TeV Muon Collider. There are a lot of attractive features about it. On the technology side, there are no obvious showstoppers, even though dedicated R&D is needed. And I would say that the path towards a Muon Collider is something that has gotten a lot of early career scientists really excited. I'm obviously very excited, but I think it's really important for early career physicists to kind of do their homework and come to their own conclusions. So this, there's a report that came out of the SNOMAS process called the Collider Implementation Task Force. I would encourage everybody to read it. And if you're convinced that a Muon Collider is exciting, then I can put you towards more resources for getting involved. And that's it.
This is a project, a long-term project, and very long term. We need intermediate steps. I mean, because you cannot last until 2070 with R&D. So it's, I mean, we are later, because we know that all the deadlines for previous colliders were not maintained, and we were always late. So what happens in between now and say the eventual construction? What else can be done by
Right,
so
so-
R&D or maybe prototype?
Yeah, so I think there are two things in terms of workforce development and physics that maintain the community in progress. The first is that if you think about high energy physics today, there's this large separation between theory, experiment, and accelerator physicists. None of my experimental students would know anything about accelerator physics if it weren't for the Muon Collider. This is the first place, the first space really where those two communities have come together and worked very closely together to build the science case for it. And so I think we have a shortage of accelerator physicists in the US and the world. The most interesting challenges are on the accelerator side. we have a lot of the same tools and shared training, we just haven't worked together historically. So having experimentalists work on the accelerator challenges is already very interesting, like that has proven to be very interesting. And in fact, that I think has been one of the most convincing things in terms of getting private funding. So there's, I think, having experimentalists work on the accelerator R&D, that can help sustain the community. I think the second thing is thinking about physics along the way. So can you, with the demonstrator, with the beam of muons, what physics can you do? With the proton target, what physics can you do? And so a lot of these, say, fixed target experiments are something people are thinking about. If you could have a neutrino factory with the demonstrator, I don't really know that at the intensities and things you would expect at a demonstrator, it would be interesting for physics, but it is certainly worth having people think about it and do those studies with sort of updating to the current assumptions about neutrino physics and where that's happening. Yes.
So the technology you're developing would also have knock-on applications in radiotherapy, right? So muon radiotherapy, I guess, is a thing. And you would be making it better for
Okay.
cancer treatment.
Cancer treatment with muons.
Yeah, no, I mean, apparently people do that.
I didn't know that people do that. That's good to know. I mean, I know about proton therapy, but really with muons,
Apparently,
even though they wouldn't be interacting nearly as much.
I have no idea.
Okay. Okay.
Well, they decay into electrons.
What it takes a long time.
Well, I guess it's a big case.
Yeah, but yeah, I think it really, I don't know. I'll Google.
I did.
So Massimo said, no, the muon, the neutrinos will, cause radiation, everywhere in Chicago will turn green. And you said, it's not a problem, just put it 200 meters underground.
Mhm.
But you also said we can reuse a lot of the existing Fermi lab infrastructure. So is the infrastructure currently 200 meters underground, or
No.
is this like a big
The
excavation?
collider ring, so the highest energy part of this accelerator complex, which would need to be in new ring, that would need to be 200 meters underground, which is not unheard of, but compared to say how deep the LHC is.
Well, in New York, you can dig a tunnel for only $1 billion a mile.
It's the receipt.
Yeah, actually.
Was it really?
So you had the question.
Yes.
Can you probe the Higgs potential with a Muon Collider? Like if FCC doesn't happen, can a Muon Collider swoop in and do some of the same measurements?
So with FCCEE, you're not probing the Higgs self-coupling any better than the HLHC is.
Okay.
With FCCHH, the claim is that you can get to say 3% uncertainty. We have no way to go. So with the 100 TeV PP collider, right? We either we stage and we have E plus E minus followed by PP, in which case the time scales become enormous. Or if we go straight towards the hadron collider, it has to be an intermediate energy. It has to be either between say 50 to 80 TeV. And nobody has really done a physics study for how well you measure the Higgs potential in that scenario. That scenario is more comparable to the Muon Collider timeline. And Muon Collider, I think forget exactly what the precision is on the self-coupling at 3 TeV, but at 10 TeV, it's better than, just barely better than the yeah, I had the 2 slides. Was it really 2 slides? Yeah, you're 3.
Oh, yeah.
Yeah. So people have only done the study with 100 TeV hadron colliders. So in terms of exactly who gets better and when this can happen is a little bit up in the air. I think part of the reason I find this much more convincing is because it's full simulation. The backgrounds are inherent. The standard model backgrounds are inherently lower. And the 100 TeV PP, any high energy PP, is not. It's just simply not a full simulation background study. And I don't know if I trust it at this rate.
Shall we wrap up and head to wine and cheese? Thank you very much.